Hello, everybody, and welcome to our October edition of the Pigment 101 webinar series. We're really excited to have you here today, and we will go ahead and get started with the presentation. Today, we're going to be talking about sort of a subject that we all deal with on a day-to-day basis. That is the pigment selection process. And in this case, I want to be able to focus on the opportunity to balance the must, wants, and nice to haves, as I like to call them, in there. Just a couple of housekeeping items here before we get started. I am recording this webinar, so all those in attendance will get the link to the recording as well as the PDF of the presentation. If you have any questions along the way, feel free to put them in the chat box and I'll address those at the end of the webinar. However, if that's not your thing, go ahead and shoot me over a note here with your question and I'd be happy to help. With that, we'll go ahead and get started with the presentation. I'm going to go off camera because it's a little bit distracting for me. So we will start with the balancing the must, wants, and nice to haves. So the colorant selection process can be a little bit difficult. It depends on how you approach it. There are ways if you are sort of, if you have the opportunity to have unlimited resources and time, you might be one of those that kind of do one selection and then move to another selection or another selection. It's sort of like a maze process. However, no one has unlimited resources and time, so it really does help to take some time up front to establish what your priorities are. And I categorize them as the title of the webinar states is the must, wants, and nice to haves, because you need to be able to get as much as you can out of your selection. However, you are not going to get all of what you would like to as much as we try. So it's really important to make sure that we bring all of the key stakeholders into the process. The formulator is going to get some ideas and a design concept from a product designer or your customer. And they're going to give it to you potentially in more of a word and description format versus something very specific. The formulator's job then is to translate that into some type of formulation to give the appropriate color and properties that is required for that end product. It's the pigment manufacturer that plays a key role in this in there because we as pigment suppliers have a very good understanding and knowledge of the pigments themselves, what they can and can't do, what they can and can offer to a formulation. So it's really key to involve the pigment manufacturer in that selection process so that you have the most successful product introduction to the market. When doing the colorant selection process, so you've heard this line many times from me, the pigment that you choose, it's only valuable if it performs like it's designed to, and also that it is requested of the application that it's used for by the customer. If it doesn't, it has no value. Functionality is something that we like to see in pigments and colorants. But the definition of functionality can be different from person to person or industry to industry. So it always is important to understand who's asking the question about functionality and what are they really looking for. In the end, the true cost of the raw material is in context of the entire formulation, so that we take a look at the cost of that colorant in its use. This opens up the door to consider the price per pound, as well as all of the properties that it brings to that formulations. So that you can meet the customer's expectations. And there are a number of examples that fit into this type of understanding. For example, there might be a pigment that you choose that has exceptional strength in there so that you could potentially use less pigment in there so your true cost is less. Or you can get some extra technical properties from that particular pigment so that you can offer something that is a little bit above and beyond what the expectation of the customer has in there. That can be of value to your end customer. So there's a lot of things to consider when you are selecting a colorant. Obviously, color and effect are kind of the starting point in that process. Obviously, application is there, and there's a number of things to consider in that area as far as the polymers that are in there. Does it need to be indoor, outdoor? What kind of fastness? Compliance is huge in a lot of different application areas. We just spoke about cost and value. And then the list of technical properties is long in there. So it's always nice to be able to get them out on paper of all the attributes that's required going into a formulation. So this is one that we always have in our webinars. It's always key to remind everybody for this one that about 75% of the performance of the pigment comes from the actual chemistry, and that doesn't change from it's pigment specific. The remaining attributes are from the choices of finishing that are used that can shift the performance in one direction or another. And those finishings take on the chemical nature, for example, surface treatments or other additives that are added in the blending step, or they can be mechanical in nature. The type of drying process that is selected for that product, or the choice of milling or pulverization that is chosen for that particular product. So all of those added together provide you with the overall performance of the pigment. Having said that, it's always interesting to make the comment a little bit more hit to home. Is really doesn't matter who the manufacturer of the pigment is. It's the chemistry that makes 75% or so of the pigment performance. So one manufacturer's pigment is the same as the other in terms of the bulk of the performance properties. It's the end process, the finishing steps, that may or may not make one manufacturer's product equal to another manufacturer's product in there. So every manufacturer has their own choices when it comes to the finishing steps. So that you'll never hear me say something that one pigment is a drop-in for another. It's always going to be an alternative. So it's a balance. And this is something that always has to be considered when you are generating your attribute list. So we want to make sure that all of your musts are checked off. Obviously you try to get as many wants and nice to haves as you can to be able to get to the end point that you're looking for. So it's balancing that pigment performance in your application that's important to do, and spending a little time up front to decide what they are and how to prioritize them is the best way to go into the process. So the rest of the presentation is a number of examples that I have where I take a look at some of these must wants and nice to haves and be able to develop formulations to go in there. So the first example that I have is something that we see a lot in powder coatings and in plastic areas. And in this case, it is a blue color, whether it's for coatings or for plastics. But the requirement would be to have extended weatherability in all aspects of weatherability. So we know a lot about UV and water and temperature with respect to exterior weathering, but a little known part of the weathering process is acid rain resistance. It's different, obviously, in different parts of the globe, how much impact acid rain can have. But in this particular example, the customer wanted a formulation that it could offer the best type of overall weathering formulations. Some of the ones are good opacity and good transfer efficiency on the coating side. And obviously, those nice to haves is the lowest cost for the performance received in here. So, acid rain is like I said, one of those kind of little known and little understood processes. However, there is a test out there that simulates a sort of an accelerated response to acid rain. It's called the fumic nitric acid test. And as I mentioned, it does simulate acid rain resistance, especially when we're looking for these end products that need ultra long durability properties. Typically, what is used is a 50-50 ratio with TiO2 is used for the test. So, Pigment Blue 15-1, the CPC blues are notoriously poor for this particular portion of weatherability. I have 6 examples of different manufacturers' blue 15-1s under here. And under this test, we see delta E's of 24 units or more in this particular area for this test. And what we see is the CPC blues are susceptible to the ozone oxidation, and then the TiO2 that's in there acts as a catalyst for that particular reaction here, and that's more understood if we take a look at these same pigments with a 10 to 90 TiO2 blend, where we see a complete washout of the color in here. So where we have delta E's in the 32s for this particular one with a higher level of TiO2 in here. So this is something that limits the usages of the CPC blues in these very, very long-term application areas where you need an overall well-rounded performance. What's happening with as I mentioned, the TiO2 acts as a catalyst for that reaction to occur because of its nature for photocatalytic degradation. So it creates these reaction surfaces that the nitric acid attacks the CPC the crystals. So we see in severe impact in coatings, which is what I showed you in the earlier slides, delta E's in the 20s. In plastics, we see delta E's in the 10 to 15 range, and I'll go a little bit more for that one. How do we improve it? So a different way to formulate around that particular property is the use of the cobalt blue in place of the TiO2. So when we do that in those same types of formulations, we see a lot less impact from that acid rain. The coatings area, we see almost half of the delta E. Still not great, but it's better. In plastics, we see a difference now between the alpha and the beta blues, where we do see about a half improvement in the alpha blues, but no real improvement in the beta blues. So understanding a little bit more, going back to the modification of the crystals, gives us a clue as to why the alphas and the betas are different. If we go back to the slide that I used in previous webinars about CPC blues, the alphas are more overlapped one crystal to the other, so that the exterior rings are less exposed in there versus the beta ones are more exposed because they are further spread out from one another. Other reasons for this one is the difference between coatings and plastics. Coatings will always have a higher pigment loading than plastics in here. So the coatings in these formulations have 4% pigment loading, where the plastics are much less at 0.1%. And then, of course, the TiO2 acts as a catalyst for those areas. So all of those combined makes that situation occur. So some data to go along with the what we see here. If we wanted to totally improved, is using the cobalt blue as a solo pigmentation in there. So in the coatings formulation, we see a delta E of just 2. Which is well below the maximum of delta E of 5 for some of specifications that are industry specific. And then with the alpha and the beta in the coatings area, we do see both of the results being about half of the original with TiO2. From a coloristic perspective, it's always nice to know where they fit, these combinations. So your cobalt blue is going to provide you a more red shade versus versus the TiO2 blends, and then of course the CPC blue and the cobalt blue will fall in between. On the plastic sides, again, we see a good function with um, with a delta E of less than 1 for the cobalt blue in as a solo pigment. And then you can see the details with respect to the alphas and the beta versions. Again, the coloristic perspective. In this case, the combinations of the pigment blue 15, 1, and 3 with the cobalt blue are very similar in terms of the amount of redness, primarily because the pigment loading is a lot less, so you don't see as much impact from the CPC blues on the cobalt blue. And the combinations with the TiO2 remain in the similar positions. However, and there's always a but, the interesting thing to note is that pigment green 7 is not impacted at all by the acid rain in here. And this is because the pigment green 7 is fully chlorinated, and that allows it to be blocked from that attack from the ozone. So in coatings formulations, all of these pigment green 7s have a delta E of less than 1 or 1 or less in that same type of test. So here's an example of 6 other pigment green 7s. So we can see that the delta E is a half to and less for these activities for the 50-50 blend of TiO2. So even though there's TiO2 in there that acts as a catalyst, the chlorine that blocks that ozone impact. The second example is in coatings, and this can be in powder or liquid. And it probably will also work in plastics as well, now that I recall. What we're the customer asked us to do is to create some RAL formulas. In this example, it's a yellow and an orange, but they really were looking for extended weatherability. They also asked to be able to have a high hiding because that will allow some options for them to get some benefit from that formulation, as well as being used in solvent and water. And of course, there's always that good value to the customer as well. So for the yellow, we formulated this with some high performance pigments, pigment yellow 154, 139, TiO2, and iron oxide. And the first thing that we identified was that the pigment yellow 139, it's a great pigment. Don't get me wrong. However, it has some limitations. 2 of those limitations are wrapped up in this formulation. The first one being the impact of TiO2. 139 is definitely sensitive to TiO2 for that photocatalytic degradation property, but it's also sensitive to alkali. And in yellow iron oxide, formulation, which has a lot of internal water present, that alkali can impact the performance of the TiO2. Yellow 159 or 154, I'm sorry, excuse me, is a great pigment. It's not impacted by TiO2. If it's one negative is that it does have a little bit lower strength than the other yellow pigments, but it's still a great high performance pigment. And so this is the formulation that we got for this pigment combination. Now, if we reformulated the color to remove those two uh, pigments, the TiO2 and the yellow 42, the iron oxide, and then replace them with using CICPs, brown 24 and yellow 53. What we're getting is a similar color position, but a lot of extra hiding and opacity for this particular formulation. And that allows the customer to have two choices to take advantage of that extra hiding. They can take advantage of that themselves by lowering the P2B of the formulation and gather that value themselves, or they could offer that value to their end customer so that they would put on less film build for that particular property. So think lightweighting, and like aerospace. That's a key one to be able to have equal hide but less film build for a lighter weight film. On the orange side, we selected, again, bringing in the yellow 139, here also orange 36 and red 254, along with TiO2. And in this particular formulation, all three of those organic pigments are susceptible to the TiO2 photodegradation in here. So we already starting out with a great formula for this particular color. However, for long-term weatherability, this is a poor formulation because of that interaction that's occurring. So same approach here, reformulating with taking out the TiO2 and replacing that with various CICPs, in this case, brown 24 and yellow 119. Again, we see similar color position, but a much higher film build. Again, options for the manufacturer of this particular formulation to either keep the value to themselves by lowering the P2B or extending that value on to the end customer with a lower film build. From a weathering perspective, we have data up to 1,200 hours for this particular one. So we start to see some differences and improvements in weatherability. This is accelerated xenon data. The blue lines are the CICP formulations to be able to start to see a difference in here. So CICPs in general, they are very versatile in their usage, and probably should start to see more and more usages for a variety of reasons. And a couple of them we just talked about in this particular example. They are very stable. They provide that good weatherability and hiding power, and they also offer a lot of IR reflectivity for coatings that require heat management. A limitation, if there is one, of course, it does have lower strength as compared to organic pigments. But again, these are inorganic pigments compared to organic pigments. The third example is a coatings and plastics example, but in the more decorative type of formulations, where we were looking for, on the coating side, a monocoat formulation with but a very extended weatherability aspect of it. And we've spoken about weatherability a couple of times here, but there's a lot of aspects of it to consider. I mentioned about some industries having standards. In the powder coating area, there's the ALMA standard, and there is the 2605 are weathering standards for a 10-year coating. Um, from a coloristic perspective, they're looking for a silver white, very low sparkle effect for that particular ones. Some of the nice to haves is they're looking for high heat stability because it does have to go into both plastics and high temperature powder coating curing aspects of it. And something that is very multiple application useful. It can go anywhere. So effect pigments, they offer a lot to formulations, and in this particular example, we are using it for as a function as well as its aesthetics properties. And how we get there is in that final layer of the platelet, we add weather treatment. And we have a lot of choices with respect to what that weather treatment is. We have chemistry differences that we could employ, how much or the thickness that we put on there. And we can also use multiple layers of chemistries or multiple chemistries in there and designing it for the application that's required. So always options in that particular layer. We talked about the TiO2 photodegradation, and it also shows up here again. And it's very important for the silver micas to have that if it's required for the application because of the TiO2 to get the silver color. It also has that negative vibe of the photocatalytic degradation. So what we did was we took a look at some chemistry variations. I talked about that in the earlier slide where we took a look at two types of chemistries of the surface treatment. And in each chemistry, we looked at three levels of how much is used. The mica itself is a very fine mica, the 1 to 15 micron size mica, so they're very, very fine. So it has very little sparkle effect. It's more a luster, more like the natural pearls that you see. From a testing perspective, we did it in two ways where we took it out to Phoenix for the ultra accelerated weathering amount where the data suggests that 1 month of ultra accelerated is approximately equal to 1 year in Florida. And then from a testing perspective, we're always looking at gloss retention, 60-degree gloss retention, and the color, the delta E from that one. So the data that I have on this slide here is the ultra accelerated, take it out to 12 months or approximately 12 years Florida. And it's the 60-degree gloss measurement. The orange line that I have here is that that industry standard of a 50% retention after 10 years. And we already start to see if we go out to that 10th month, we see one of the formulations falls off below that line. The remainder is above the line, and one in particular is still maintains in that 95 plus range after the full 12-month period. If we look at the delta E in that same time frame and those same 6 chemistries, for the delta E, again, the orange line is the industry standard for that one, a delta E of 5 or less after 10 years. So in this particular case, we start to see at the 10-year period, there's a couple of formulations that fall off out to the 12-month period. Only one of the formulations maintains the delta E of 5 or below. For Florida, we have data now out to 4 years. And for the Florida aspect of it, there are two lines on this chart: the 10-year line and the 5-year line for that particular standard. And in gloss retention, at the 4-year mark, again, we see one formulation already fell off for the 10-year. The remainders are fine. Now, if we extrapolate this data out to the 10-year mark, we see that one formulation that was at the best position still maintains a 95% loss retention. The red line that you see on this chart is the control, which is the base color without any pigment in it, any mica in it at all. The ultra accelerated predicted a gloss retention of 96% at the 10-year mark or 10-month mark. So these two appear to track fairly closely. Again, it's a big extraction in here. We'll take these out to 5 years for the completion of this study. If we look at the delta E for the Florida aspect of it, the red line up here again is the industry standard. In this particular case, the 5-year and the 10-year have the same delta E of 5 or less, and so far at 4 years, the all 6 do fall in place for the delta E. And again, extrapolating the best one there out to the 10-year mark is a delta E of about 3.5, 3.75. The ultra accelerated predicted a delta E of 4. Again, a fairly decent track for this prediction. The fourth example is for liquid coatings. Here we're looking for our customer is formulating a coatings line, and they really want to minimize the toolbox that they're using. This particular one is a solvent-based formulation. They're looking for high loading for their pigments, and they are looking for one or maybe two dispersants for all their green and blue pigments in there. So, and obviously they're looking for the best types of properties. So they're looking for low viscosity, high strength, and highest transparency. In other words, they're trying to get as much out of the pigment as they can in their formulation. So of course, from a liquid dispersion steps, the pigment has to be wetted first, then it has to be ground to make the smallest particle size possible, and then once ground, they have to be stabilized so they don't come back together. There's all types of dispersant out there to be able to use. Ideally, you would like to be able to match up the dispersant to the pigment chemistry and the surface treatment type, but what that ends up happening is you have a very large toolbox, which is not an optimal way to run your business. Basically, you'll have a lot of raw materials in your system that you have to deal with. So ideally, we want to be able to select something that works the best for this set of pigments. So what we did is we took a look at an alpha blue, the pigment blue 15-2, where we took a look at a number of dispersant types from a chemistry perspective and combinations with others. And what we found was there were a couple of options that provided the lowest viscosity, which was one of the parameters that we were looking for. From a transparency perspective, we had one combination that did have a much better performance with respect to transparency than the others. And then lastly, from a strength perspective, there were two that stood out with a much higher strength than the control or the other formulations. So taking all of that into consideration, we came up with one combination that worked the best for this particular alpha blue. Then we applied it to all the other blues and greens in the space. So here we're going from one alpha blue, the 15-2, to the other alpha blue, which is the 15-1. And in this particular case, what we see is the Solo BicJet 9152 um, uh, had a more of a negative impact in terms of viscosity when we went to the 15.1, where the other two options tended to be about the same. So the grid on the charts here are the same for each one of them. If we went to the beta, from alpha to beta, so the 15.2 to the 15.3, we see two of the options here now have a much higher viscosity than the third one for that option. And then lastly, if we take a look in the blue space to the alpha to the beta, but both of these being the surface treated versions, the 15.2 to the 15.4, again, we see some differences between two options, where in one case there's a better performance in the beta 15.4, and in the other case a lesser improvement for the other one. And the last in the space that we were asked to take a look at was the green 7. So we see one formulation where the combination or the solo dispersant was not as good for the green 7 as the other two. So what this allows us to do is come back to the customer and say, okay, these two dispersants, whether they use solo or the combinations, are the most optimal for these 5 blues in that space, as well as the green in that space. So that allows the customer to have a minimum number of dispersants in that system. And the fifth example is in plastics, and specifically for fiber and film. This customer needed to have pigments that could have a very high dispersibility properties about them, because they could not afford to clog the spinnerets when they make the fibers. They also do need to have a high processing throughput to be able to create those fibers and of course the film itself. Um, would like to have a wide color range of pigments available to them, and as wide a polymer application as possible. So what that ends up doing is creating what I call a regular grade for plastics and a fiber and film grade for plastics. And the difference being is how they're tested, and especially at that towards the property of dispersibility. And in plastics, that's tested by taking a look at the filter pressure value. However, for the fiber and film, it needs to have a better uh, filter pressure value with a smaller mesh size. So in this case, a 10 micron mesh size versus a 25 micron mesh size for regular plastic application areas. The other two parameters that are very different is the test time is longer. Again, we're looking for that productivity, long run times, as well as the amount of pigment that has to pass through the test. It's twice as much as the regular plastics properties for plastic pigments. Some examples in the yellow space, the pigment yellow 191, the KF, which is how Sudarshan signifies the film and fiber grades of the pigment yellow 191, the Sudafast 129. We see the comparison of the filter pressure value on the 10 micron mesh as being much lower than the regular grade. In the film note rating, we also see an improvement there as well for the fiber and film grade. In the red space, pigment red 170. Again, we see a much improvement in both the filter pressure value on that 10 micron mesh, and also a significant improvement in the film note rating as well. And in the blue space, lastly, is a pigment blue 15.3, where we see a very marked improvement in the 10 micron mesh dispersibility area, and also an improvement in the fiber and film. So how do we do that? There are two places where we alter the finishing. Remember, I go back to the finishing step that shifts um, the performance in one direction or in the other. So the choice of drying method and the choice of milling method allows us to create a product that is softer, easier to disperse, and also potentially finer and a smaller particle size distribution as well, all in an effort to improve that dispersibility. So from a color and property perspective, our KF series is growing, continues to grow, so that we have a good wide range of color available to the customers that need it. And lastly, the last example that I have for you is also in the plastic area, where with everyday sourcing and technical are always facing issues with supply and availability of pigments, especially in the FDA compliant areas. So we had some customer requests that came in that were looking for FDA compliant options to be able to help them with some supply constraints that were out there. But of course, we wanted to make sure that we had at least equal or potentially better technical performance, as well as equal or better value in use. So a couple of examples that I have for you. Oh, before we go there, FDA compliance looks differently, whether you're the pigment manufacturer or the end user. From the pigment manufacturer's perspective, there's always going to be a significant monetary investment when we do apply for FDA. And also there's a significant time period that is required to be able to potentially receive that compliance aspect of it. So there's always got to be a good business case for us to be able to go that direction. From the end user perspective, of course, you need to make sure that you meet the regulatory requirements for your industry. You're going to want to be able to reserve that supply of the compliant product so that it can be directed towards those mandatory areas. It may mean that you potentially could have two products of the same color index, one that's FDA approved and one that's not. However, that can be lead to a potential mix-up of one or the other, and that's one thing that, as a producer, that you definitely don't want to have that mix-up in your system in there. So we wanted to be able to have options available. So the first one is a yellow 151. And in this particular case, we were able to get to that color space using the pigment yellow 138 and yellow 191. And of course, some TiO2 to be able to get to that space. So we're able to provide an equal color position that still maintains the FDA compliancy. It has equal technical performance. And one of the nice to haves that we were able to achieve is we got to that place with a lower pigment loading than the straight 151. The other example that we have is also in the yellow space, pigment yellow 180. Again, we were able to match it with a base of pigment yellow 138 in combination with yellow 110. And TiO2. And likewise, we were able to maintain the FDA, equal technical performance, and in this case, also a lower pigment loading in there, so some additional value in use for that particular formulation. Not only that, but also options. So we'd like to thank you. Of course, if you have any questions or need any assistance, you can reach out to any one of our team. We always are happy to help with whatever your needs are. We will not be having webinars in November and December, so let me be the first one to wish everybody a good Thanksgiving and a Christmas and holiday season. And we will pick up the series in January in the new year. So with that, I'd like to thank you once again. We really do appreciate everybody's joining us and encouraging us to keep these going. It really means a lot to us. And at this point, I'd like to open it up to any questions that you might have.